This microburst video contains segments extracted from the Windshear microburst portion of the AAMP presentation. It begins with examples from the microburst accidents at Charlotte and at Dallas-Fort Worth, which will be used to define the air mass effects on your airplane. These examples clearly demonstrate that a microburst encounter at low altitude or near the ground will require the crew to work together in order to extract maximum performance from their airplane. We're going to start jumping into some real-world issues. We're going to take the body of knowledge that we have developed to this point and start to apply it to things that are happening out there. First, we're going to look at air mass anomalies as a grouping. We will look at microburst, wake turbulence, and mountain wave activity. Starting with microburst. Now, my issue with microburst, as you might imagine, is the performance issue. Okay? How do we get max performance out of our wing? But before I can get to my performance issue, I am told by my boss that I need to talk about some fiduciary things here. And the first of those is avoidance, i.e. we do not do this on purpose, of course, and every pilot in this room clearly knows that we're not going to start an approach when we've got a line of red thunderstorms across the final approach course, or if the wind shear boundary alert at Denver's got a 70-knot differential. Well, of course we're not going to start those approaches. But on the other hand, I learned another thing I learned preparing for this is I studied 4 microburst accidents in detail. And I used to say that this would never happen to me. I've been flying for too long. I got too much experience. There is no way man is going to fly into a microburst. Well, I got to tell you, after I studied those 4 accidents, I came to the clear conclusion that those crews had nowhere near adequate input not to start those approaches. In my opinion, I'd have been there every time. So with that in mind, then, we know what we learned from that, what I learned from that, is this is going to happen to us. Sometimes this is going to happen to some of us. So then the question becomes, can we deal with it? The good news is, the answer is clearly yes. The worst microburst I studied, the thrust-to-weight ratio airplanes we fly today, can win the fight. But they have to be flown properly, which is the issue that I'll talk about in a minute. Buy insurance. What's that about? In all American Airlines manuals, it tells us that if we're going to start an approach in unsettled weather conditions, I don't mean thunderstorms, but you know, rain showers in the final approach zone and so on. If we're going to start an approach in unsettled weather conditions, what do our manuals tell us we can do to protect ourselves on that approach? Sure. Exactly. I heard both of those answers. The first one is they say we can increase our airspeed up to as much as 20 knots above VREF, right? The other thing we can do, which puts energy in the airplane, right? Kinetic energy. The other thing that we can do that's even better is some fleets allow us to reduce flap settings on approach on this kind of weather. Now that is really smashing the kinetic energy in the airplane, because if you reduce flap settings intentionally, 2 good things happen. First, you reduce the drag if you should attempt to escape. Second, you move your VREF up for the lower flap setting, to which you can add another 20 knots. Now you've got some real kinetic energy in this plane to fight the bear if he comes. Good stuff. On takeoff, likewise, if we think we're taking off in unsettled weather conditions, what are the things we can do? Well, the first thing is, if you're scheduled to go standard, as you know, go max power. The other thing is we're allowed to add airspeed. Which airspeed can we increase, V1, VR, or V2? Yeah, VR, right? V1 and V2 are inviolate performance numbers. But VR, we can move around. And so we're allowed to increase VR as much as 20 knots or runway limited VR, whichever is less. Good stuff. Again, put kinetic energy in the airplane to fight the bear if he comes. Okay, having done that, then we come to bullet 3, recognition, and I got that wind arrow symbol there. For those of you who don't have wind arrows, don't worry about this. But those of you who do have wind arrows in your airplane, that is a wonderful tool. That is a real-time instrument coming off your ring laser gyro platforms, whatever platform you use in your fleet. It is giving you real-time information about what the air mass is doing to the hull of your ship. Real-time. So if you're entering a microburst, you will see that arrow start marching toward the nose, and you'll see the numbers starting getting bigger, saying, look what's happening to you. And that will be obvious much quicker than what you can get from your pedostatic instruments cognitively. Neat tool. If we use it in unsettled weather conditions, it'll give us an early warning. Okay, but now as in our manuals, when it comes to the recognition issue for all of us, we have this list of parameters in our manuals that tell us what's presumably unacceptable, which is, plus or minus 15 knots on the airspeed, plus or minus 5 degrees of deck angle, plus or minus 1 dot in the glass. Well, I don't know, maybe. I suspect, though, the highly experienced pilots in this room rely on experience. And by that I mean I think we're out there doing our job. Our job is get these airplanes in and out. Even in the face of adversity, we do that. Not big thunderstorms, but, rain showers, unsettled weather. That's what we do. We get these planes in and out. And we're out there banging around, in rain showers or something someday on an approach, and we're working our way in, bouncing around, doing our job, trying to stay on the ILS. But there'll be some point in that approach where our vertical and lateral path control becomes very tenuous, and the hair on the back of our neck starts to go up, and our experience tells us this is getting too bad, let's get out of here. That's probably reality, isn't it? Now, when we make that decision to get out of here, what do? That's the question. Now, in a minute, I'll show you the red box that outlines what we do, but let's talk it through. What do? The pilot flying, what he should do is take the throttles and physically advance them fully forward. If he needs to toga Windshear guidance, he should toga on the way and get it programmed up. When he gets the throttles full forward, disconnect them. All fleets, all the way up and off. In 2 of the microburst accidents I studied, the auto throttles were left engaged. In both cases, the auto throttles retarded the power after the attempt to escape to one or another cue. Don't allow that to happen. Put them up, turn them off until you're done with them. With the very same hand that you push the throttles up, you should always come back and be sure the speed brakes are stowed. Because I don't care what the scenario is, anytime you physically push these full forward, I guarantee you don't want those out. So make it a pattern. Full up, disconnect, confirm spoilers stowed. That's what you do with your throttle hand. With your flying hand, disconnect the autopilot and pitch to 15 degrees or V-bar guidance if you have it. The V-bars will go to 15 too, so it doesn't matter. Essentially, they're both in the same place. All fleets. Okay, that's our starting point then. Now, you'll notice that in our manuals it tells you that you want to stay at 15 degrees as long as possible. Now, why do we say that? Because many of our airplanes have an adequate thrust-to-weight ratio to climb and maintain speed at even higher deck angles. But yet our manuals tell us stay at 15. They make a point of it. And the reason that is because when you study microbursts, what you realize is that what you need to win is kinetic energy, not potential energy. I.e., potential energy in the form of altitude doesn't do you near as much good as kinetic energy in the form of airspeed, which is why we tell you to stay at 15 as long as possible. Okay? So you're holding 15 degrees, the pilot flying is, and he's got the full thrust vector in. Now, he stays there as long as he can. Now, what is it that's going to tell him he needs to do more than he's doing now? The threat. The threat's going to tell him, isn't it? It's the ground. If the ground is coming, he's got to do more than he's doing now. Who's going to let him know that? The pilot not flying. The next bullet. The pilot not flying is a key player in this game, equally critical. His job is to immediately get on the radio altimeter and the IVSI and let the pilot flying know how he's doing relative to the threat. The threat is the ground. There should be no mention of airspeed. Guys and gals, with all your experience, come with me on this and think this through. Here's an airplane. Here's the ground. You have X amount of energy in this airplane, and the throttles have been fully applied. The energy part of this equation is a given. It cannot be changed. So why talk about it? To win this war, you're going to end up flying angle of attack. You don't care what's on your airspeed indicator. You can't change that part. Okay, so here we are. 15 degrees, full thrust rate, and this guy's holding on. If the pilot not flying is saying, hey, you're at 400 feet, oh, you're climbing, you're 450 now, hey, you're doing good, you're climbing out of 500, well, it was wind shear. Great. Now let's watch microbursts. We've got everything in. We're at 15 degrees, a deck angle, full power. Pilot not flying is saying, hey, you're at 400 feet. You're hanging in at 400. You're doing good. Hey, you're at 440. You're doing pretty good. You're doing pretty good. Well, what's going to happen in microburst is you'll enter the headwind portion, and next, as you know, you will transit into the downburst portion. The air is coming down and going out, as I will show you in a minute. As you enter into the downburst portion of the microburst, you will take up a sink. It's fairly significant relative to the ground. Okay? As you enter the downburst portion, you'll start sinking. The pilot not flying will immediately start hollering, hey, you're sinking, you're coming out of 400 feet, now sinking 400 feet a minute, da-da-da. Well, what do we got to do here? Pilot flying, what do we got to do? Pull back on the pole, right? And up comes the deck angle and alpha. You're coming up, and we're trying to stop the sink. You go to 20 degrees of deck angle, and he says, man, you're still sinking. You're coming through 300 feet. You're still sinking 500 feet a minute. 25 degrees. Hey, you're still sinking 30 degrees. Do not hit the ground, rule 1. See? You do what it takes to stop that sink that the shaft sets up. Having done that, you'll get it stopped. If you get aggressive, you'll get it stopped. And then you get it stopped. Let's say you get it stopped around 200 feet AGL, and now you're holding maybe 25-degree deck angle or something, and you're hanging in there in the downburst portion, and the pilot not flying is telling you you're holding 200 feet, you're doing good, you're doing good. Now, no matter which way you turn in a microburst, you will enter a tailwind. There is no other way out. You must enter the tailwind. When you enter the tailwind, depending on the microburst accident I studied, you will lose between 38 and 52 knots off your airspeed indicator. If you are flying airspeed, the next thing you will do is lower your nose. Shortly thereafter, you will enter the ground. On the other hand, if you could not care less what is on your airspeed indicator now, and as you enter the tailwind portion and you hear the pilot not flying telling you you're trying to sink again, you will increase angle of attack to counter sink. As you enter the tailwind portion, those of you who have PLIs, you will see your PLI start to come toward your nose. Or with VSS bars, you'll see them rising toward the index. If you don't see those things, you're coming toward stick shaker alpha. You just can't see it coming. But it's coming. As you continue to work into the tailwind portion, your alpha will keep going up as you try to stop sink. Finally, you will get to stick shaker, PLI, VSS bar, CL max, angle of attack. You're there. Stay there. It's the best you can do. Hold it. Ride it. Hold that alpha. The pilot not flying will be saying, hey, you're hanging in there. You'll be burp, burp, nudging the shaker, burp, burp. Hey, you're great, you're great. You're holding 200 feet. Way to go, way to go. Now watch this. Hey, you're hanging in there. You're doing great. Wing drop. And the pilot flying takes the yoke and goes, yeah, with the yoke. Oh, no. What did we just do? We just threw up all the spoilers on the high wing, dumping the lift we had intended to save our lives with. We dumped it. She'll start to shut her down. She'll start sinking again. The pilot not flying will be screaming, geez, you're sinking again, you're sinking again. Wing drop, yoke, spoilers, shutter, sink. We're gone. We're gone. We're trying to fly this plane at a very high angle of attack using roll controls only. Watch this, same point. We're in the tailwind already. We're riding right on the stick shaker, hanging in there at 200 feet. Same thing happens. Wing drop. This pilot applies rudder. A small amount, smoothly applied, of coordinated rudder will lift the wing. Net, it increases the lift on the low wing, decreases it slightly on the high wing. Net, it preserves the same total lift vector, as opposed to throwing up all the spoilers. In doing so, he will get a better roll response and preserve lift. So now the pilot not flying says, hey, great, you're still at 200 feet. Way to go, way to go. Wing drop, rudder. There'll be some aileron, but rudder and lift. And hey, you're good. You're 220 feet. You're doing good. One crew dies, one crew lives. Same microburst. The crew that dies is dumping lift in a lift critical situation and reducing the lift vector. That's highway maneuvering. Then we come down here to this respect the stick shaker. What's that all about? I'm going to submit to you the airplanes we fly for American Airlines essentially have fixed stabilizers. Because you see, when we entered this event, we stopped trimming. And we should have. That's fine. But when we stopped trimming, we've been flying the airplane with just the elevator. That stabilizer is still trimmed to 150 knots, let's say. And as we work through the tailwind portion, we may be down to 100 knots. And we're holding it right there at that angle of attack with elevator only. You know, keeping the elevator back and holding it in here. Well, what would happen if to someone's, let's say, saying your airspeed's low, or the stick shaker itself, if we were to respond with, instead of just curling our wrist in and out, we were to push the yoke forward. If we push the yoke forward, we would initiate the moment. It's a static stability issue, really. It's going to start down. And once it starts down, even though you come full back, that little bitty elevator will not stop it. It will now seek trim speed to that great big stabilizer. So even though you're holding full back on that elevator, the nose will continue to the completion, and you get there first. You'd have been better off to stall the plane. At least you'd get there last. This word yellow, word escape up here, what we're saying here is someone in the cockpit, if you get into one of these bad deals on final someday or wherever, in Microburst, the word that should be spoken is, we're going to escape, which sets the mindset. The guy flying goes to the fight mode. The guy not flying just tells him how he's doing relative to the ground. This is different. We must announce different. Okay, this is in all of your manuals now. It's a red box item. It's relatively new to your manuals as a memory item. And this part of it's all generic. It applies to all fleets. Now, on some fleets, there'll be a step before this, you know, that tells you to toga if you want your Windshear guidance bars up there or whatever. But this is a generic part that applies to all fleets. Now, I'm going to tell you, as I turn around and face you, I cannot recite that procedure. Okay? But I know what it says to do. Now, you know, we write these things this way to get them generically on a certain number of lines. But what does that thing say to do? Well, what that thing says is the pilot flying will take his throttle hand and go full power, physically full power, then disconnect the auto throttles, and with the same throttle hand come back and be sure the spoilers are stowed. With his flying hand, he will disconnect the autopilot and pitch to 15 or V-bars. That's what that says. I find it much easier to remember what I do, not only for my memory, but for practical application. Call-outs. As I mentioned earlier, all reference to airspeed has been removed from the manuals. What we need to know is how we're doing relative to the threat. The threat is the ground. You might find this interesting. The NTSB, as I've mentioned, especially in my Washington courses, I've had 10 or 12 NTSB, either members or investigators. And in this example, I had two different investigators in two different classes that had been the lead investigator on two different microburst accidents. And what they told me was very interesting. They said they noticed that when the airplane transits from the headwind portion to the downburst portion, there is a significant pressure change. And the pressure change goes from high to low. See, so whether you're climbing or sinking relative to the ground, your IVSI will show a climb in that transition. Now, there's a thought. It's transitory but confusing, isn't it? So what that taught me, though, and what I learned from that, is this is the bottom line, isn't it? The radio altimeter is the bottom line. If that radio altimeter is decreasing, then you are sinking toward the ground, or the ground's rising toward you, okay? But both of them are the same problem. The radio altimeter doesn't lie. If we're at higher altitudes when we encounter a severe air mass event caused by convective activity or perhaps mountain wave, our response to the airplane sinking should be different than the escape maneuver. Since the ground is not a threat, aircraft control should take precedence over loss of altitude. We should keep the angle of attack on the wing well inside the envelope by unloading, rather than fly at or near stick shaker alpha in an attempt to maintain altitude. I know we are all concerned about other air traffic and the potential for a midair. However, wouldn't you rather be under control when your TCAS issues an advisory? That's something called a wind field diagram. This came out of the Charlotte microburst accident. Last year, Charlotte US Air, MD-80 guy at Charlotte. There was a lot of interesting stuff in this NTSB accident report, but I thought this one would be the most useful for you. This wind field diagram is created after the fact from numerous data points. It's considered to be reasonably accurate. It will show us the sheer power and magnitude of this microburst. Okay, all these little arrows are the wind direction. This is done at 300 feet AGL. I don't relate well to meters. I don't know about you. This is all meters all around here. So for dimension, let's use the airport. This is the Charlotte Airport. That's a 10,000-foot runway right there for dimension purposes. This red line is the ground track of that MD-80. The MD-80 is right here when this microburst hits the ground. He is right here when he hits the ground. Okay? This microburst is 30 seconds into its life. I didn't know this. Did you guys and gals know that the average life of a microburst is 8 minutes? 8 minutes from the time the downshaft hits the ground and goes out till it's gone. How do you anticipate something like that? How do you predict it? See? In my opinion, these poor guys are just in the wrong place at the wrong time. And they're right here when this thing hits the ground right in front of him. This microburst you're looking at is 30 seconds into its life. I'm going to advance this slide in time increments of less than 2 minutes. I'm going to hold my light at the point where he enters this microburst. Now I want you to watch this puppy grow. Okay? I'm going to hold it at the point where he enters it as best I can. Now watch this. Bang. 2 minutes later. A little less than 2 minutes later. Look at that thing grow. Now watch this. A little less than 2 minutes after that. Look at that thing. That's a 10,000-foot runway. This is a serious air mass event. Well, what happens? Well, he meets this thing, as you can see, coming at him half as fast as he's going at it. The result of that is, as you enter a microburst, the first thing that happens is you enter a headwind. When you enter a headwind and when you're flying, as long as you get your hands on the controls, even with the autopilot on, as long as you get your hands on the controls, what's going to happen? Well, the yoke's going to go forward, and these puppies are going to go backward. And you're going to be sitting in there like, I don't usually sit in here like this, you know. Which is kind of your first clue bird, isn't it? Your first clue bird that something's going awry here. They got the clue bird early on and made a timely decision to get out of there. Essentially what you watch going on, though, is a kind of a go-around. And so as they go through that process, they do fairly well as they work their way through the headwind portion. And then, as you can see, the next thing that happens is they enter the downburst portion. The air is coming down, this vertical shaft, and then going out. As they enter the downburst portion, of course, they take up a sink. Now, this crew aggressively fought that sink. They did a pretty good job, and they stopped it before they got to the ground and stabilized. But then, you see, no matter which way you turn out of the downburst, you must enter a tailwind. In this accident, the wind factor, tailwind factor takes 38 knots off the airspeed indicator. And they lower the nose. Shortly thereafter, they enter the ground on speed. On speed. Let me say right up front, these two pilots may be the best two pilots on the planet. And probably are. I don't personally know them. However, if you are not trained to fly the way we're talking about right now, how can we possibly expect you to do this out there in the real world when it happens? Okay, let's look at another microburst accident because it's going to teach us some more things about performance. This is a video of a microburst accident that happened at the Dallas-Fort Worth Airport. It's a Delta 191 coming into land. Coming into land at Dallas-Fort Worth. This will be a little clearer when we get it going here. It'll brighten up a bit. I just took clippets out of that film. Okay, the first clippets will show you the crash site here by the tanks. This guy is trying to land to the south on what was then 17 left at DFW. I will take some clippets of the crash site taken from a helicopter and then the tower cam, and then we'll take some clippets of the weatherman in Dallas-Fort Worth. Listen to the weatherman saying there were essentially no clouds over the airport when this guy comes over Blue Ridge. I mean, how could he decide not to start this approach? Listen to the weatherman saying, I didn't even see this on my Doppler radar till 10 minutes after the crash. Listen to that stuff first, the weather stuff.
Tower Delta 550, Evans with you, final 17 left. Where's the crash track? They're coming. Report of a heavy jet just crashed off the north end of the airport.
Rest carefully moved the rest, putting their bodies on stretchers and taking them a distance from the main crash site. According to officials, the Delta jet was en route nonstop from Fort Lauderdale to DFW Airport and was to go on to Los Angeles.
Most unusual because 15 minutes before 6 o'clock we had looked at the radar and there was nothing there. I mean, this was a rapidly built up thunderstorm. It came up very, very quickly, and as it did, we caught it with the Channel 8 precision radar. This is actually about 10 minutes after the time of the reported crash, and you can see there was a most intense thunderstorm indicated by the red area right over the east side runways, the Dallas County side runways of DFW Airport, and right at the precise location where that crash occurred. We can take this shot up just a little bit closer, and as we do, you can see this core area of red and then the little flecks of white. At the particular angle the radar was at, that would indicate a very heavy downpour of rain in that particular area. There may have been hail, and we've heard reports of lightning. We did some minor Doppler analysis, and quite frankly, it happened so quickly we didn't see a lot, but we saw no significant rotation from the National Weather Service radar in Stephenville, and as we follow the motion, there is the storm. It just died away within about a half an hour. Another storm over Fort Worth was gone, and then there was some out west, and tonight there's nothing left.
Let me say that I've traveled around the country talking to all our pilots. I was not personally there that day. However, I've met many of our crews that were that day as I've done this program. And all of the stories they tell corroborate one another. Two of the best ones, I think, are as I had the captain and the co-pilot from the airplane that was 2 ships behind this Delta. In other words, the Delta, an airplane, our guy. And on 2 different meetings, both the captain and the co-pilot said the same thing, and that was they had no incentive to do anything but come in and land. They could see a little rain shower there, you know. They could see through it to the runway. The bases were up at 6,000. They were coming in to land. No reason to do otherwise when this guy splashes right in front of them. The guy on 18 right said the same thing. I had another captain that was number 1 for takeoff on 17 right, you know, 90 to the runway, looking toward the tanks. He's planning on taking off as soon as he gets a clearance. He has no incentive to do otherwise when this Delta splashes right in front of him. Now, he said 8 seconds later, his entire airplane was rocking on its legs, and with the parking brakes parked, the airspeed said 75 knots. This is an insidious event. It's going to happen sometimes. Okay, as we go through this, we're going to do it twice. What we got here is 2 runs at this. Both of them will have the body angles. Both of them will have the body angles of the airplane visible. And in the first run in this block, you will have the CVR data printed as you hear it audibly. On the next run, you'll have the body angles visible, but in this block, you'll have all the DFDR performance instruments. On the first run, what I want you to do is listen to what's being said and read it. I want you to tell me if you see a phugoid type mode maneuver occur when it occurs. And tell me, why did that happen?
About 1,000 feet. 762 in a barrel. I'll call him off for you. North America 178, turn the corner. Yes, sir. Everybody around the corner when you're number 1. Major 136, contact.
I'm going to lose it all of a sudden. There it is.
Go on.
Push it up. Push it way up. Way up.
Way up.
Way up. That's it.
Wagon 626, over takeoff. Speed wheel. 586 in the position 017 line. In position hold.
Pull up. Pull up. Pull up. Way up. Pull up. Pull up.
Right turn off. Traffic's a mile per hour.
Okay. Did you see a phugoid? Yeah. It starts at 650 feet, so he's got plenty of altitude, and he's out of it again at 250. I mean, that didn't get him. You know, he had enough altitude to work it through. But you see why it started? See why? Yeah, exactly. What's my VREF? It turns out it's the co-pilot talking to himself, the first officer, who is flying the airplane, and he says, he says, what's my VREF? And he looks down and sees his speed about 8 or 10 knots low, and he pushes the yoke forward. And that starts it. I know that because I can time in control column position to the same second. Now, what we're going to do next is we're going to look, I'm only going to do this once, so you will not have time to watch everything. Do not try to watch the wind field vector. Don't try to watch control column position. Don't try to watch EPR. I will tell you right now, if you were watching EPR, you would see that the pilot's got full power on these engines. You will also see that subsequently the auto throttles will retard the power, in this case due to a high speed cue. Don't let that happen. Up and off until you're done with them. What I want you to watch on this run is the body angles of the airplane and these two things, AOA and airspeed. I hope at this point you will agree with me. Airspeed is energy. And AOA is lift. And we're going to watch energy and lift play out in this scenario. On the energy indicator, we have the VREF for the airplane right here, and then 10-knot increments. Right now, he's about plus 15. On the lift indicator over here, we have an analog angle of attack indication, and that bar right there is stick shaker alpha, what we know as CL max, okay? And then 24 under the 25, that would be stall alpha or flow separation. By the way, is this interesting to you? The flight data recorder has an analog angle of attack indicator. And further, the NTSB says that one of the channels on our airplanes must be angle of attack indication. Because after all, when we go to investigate an accident, how can we possibly tell what happened if we can't see angle of attack? Think about that. Isn't that interesting? All corporate jets fly with it. Now all military aircraft fly with it. And we can't see it clearly. We have some tools, but we can't see it clearly. Now let me tell you something. The NTSB is with us. They are recommending they should be in all airplanes. Okay. What we're going to do then is watch energy and lift play out, okay? And at the end of this scenario, I'm going to ask you, did this crew extract anywhere near all of the energy or all of the lift in this scenario? Here we go.
Three-phase one, you copy the cross? Yes, sir, we're on the way back to 351. Thank you.
About 1,000 feet. 762 at a barrel.
Plus 25. He's doing real good.
Yes, sir. Everybody around the corner when you're number 1. Major 136, contact.
I'm going to lose it all of a sudden. There it is.
Go on.
Push it up. Push it way up. Way up.
Way up.
Way up. That's it.
Wagon 626, over takeoff.
Speed wheel.
586 in the position 017 line. In position hold.
Pull up.
Pull up.
Pull up. Pull up. Pull up.
I'm going to freeze this here at 50 feet. I'm going to ask you two questions. Is there any energy in this airplane? Is there any lift left on this wing? You know, there is no harm, no foul on this crew. There really isn't. I mean, do you see how purely fast this happens to them? You see how quick that happened? If you're trying to fly by some conventional cross-check and a conventional means with no one clearly identifying to you how fast the ground is coming, rest their souls, I'd be there too. But if one pilot were purely focused on extracting all the lift out of this wing and the other were purely focused on how he's doing relative to the ground, our non-engineering study shows that this plane would have never come below 500 feet AGL. If you should encounter a microburst on departure or on approach, it may require you to extract maximum performance from your airplane. The microburst training you receive in the simulator will be both challenging and rewarding. It should prepare you, as a crew, working together to successfully escape from this powerful and potentially catastrophic air mass anomaly.
$50, $40, $30.